Let's move to analysis model, rigid object under a net torque. Alright, so if we consider an object here having mass of m, is moving in a circular path, experiencing angular motion or circular motion. Okay, at this instant, this object experienced 2a. Still remember? Based on Newton's second law, F equivalent to ma. So if we are referring to the at, we have Ft equivalent to mat, and we know that torque is equivalent to F times R sine theta. So for this case, okay, for the R is here, right, and the F is here, it's sine 90 degree, which is equivalent to 1. Right, so our F itself, Ft, tangential force, is equivalent to mat times R. So the at itself can be substituted with the information of angular acceleration, which is at is equivalent to R alpha. Okay, then our equation will be like this. So simplify this equation, we will have mr squared times alpha, whereby mr squared here going to be simplified as I, capital I, which is known as moment of inertia. This is a similar analogy to the mass, but not exactly the same, because we are referring to the angular or circular motion. So torque is equivalent to I alpha in comparison to sum of F equivalent to ma in linear or translational motion. So similar analogy but not exactly the same means that moment of inertia here, the I, is a measurement, is an indicator to how big, how massive the object, and how hard to move the object due to its mass as well as position. Right? It's not only mass, it's also due to the mass with the position. For this case, okay, m is indicator of the amount, the content of an object, giving us the idea about if the m is very big, means that the object is very hard for us to move it, to achieve the A. Right? So almost the same, but not exactly. So sum of torque equivalent to I alpha, analogy to sum of F equivalent to ma in translational or linear motion. Alright. Then if we have numbers of objects combined within undefined shape of object, okay, so we have to add up, we have to analyze one by one, and we have to do part by part, and finally add them up like this. Okay, where finally we are going to have sum of torque external on the system is equivalent to I alpha, where I is actually sum of mi ri squared, means that we have to add up every single moment of inertia for each of the object. This is actually similar analogy to the sum of x external equivalent to ma, where a is the one experienced by the center of mass for that particular object. Okay, normally we didn't highlight on the cm here because it is understood that the a will be visualized at the center of the mass for the object, right? Because we mostly or commonly use rigid object. If you are using non-rigid object, for example, a liquid or gas, okay, some portion of the object or system might move first, isn't it? Okay, some part of it might move later. So means that the A is not a constant. So that is why we are not going to apply this kind of formula. So here is list of moment of inertia for different type of object. you have to be able to recognize which object to be applied, okay, in your problem solving. So if you see here hoop or thin cylindrical shell, the moment of inertia at the center, with the condition that the axis of rotation is at the center of the object, okay, passing through the object like this, I at the center of mass, okay, is equivalent to mr squared. For solid cylinder or disc, okay, I at the center, the axis of rotation is at the center of it, is equivalent to half mr squared. And if we have hollow cylinder, okay, I at the center is equivalent to half m in bracket, okay, r1, okay, squared plus r2 squared. How about if you have a long thin rod with rotation axis through center? Okay, if that the case, then I at the center of mass for this thin rod, okay, is 1 over 12 m L squared. How is it? Sometimes it's 1 over 12, sometimes it's half, sometimes it's 1/3, it's 2/5, 2 over 5, 2 over 3. Why is it so? It's actually, it is derived based on this equation. Okay, particularly. So for this case, okay, long thin rod, but then the axis of rotation is at one end of it. Okay, the I of it is 1 over 3 m L squared. Okay, if you have a rectangular plate and axis of rotation is at the center of it, then 1 over 12 m, okay, a squared plus b squared. If you have solid sphere, okay, I at the center is equivalent to 2 over 5 mr squared. If you have thin spherical shell, then the formula will be 2 over 3 mr squared. Don't worry, okay, the table 10.2 here going to be given in your test or your exam. Right, now we want to take a look on more detail on the sum of torque external is equivalent to I alpha, which is torque external if we refer to this situation, okay, where we have a disc, okay, pulley, and then you have torque due to two kind of forces here. Okay, this is torque number 1. The possible rotation, okay, due to torque number 1 is counterclockwise. Okay, the possible direction of rotation due to torque number 2 is clockwise direction, right? And this is the alpha experienced by the object, right? So if we apply this, sum of torque external is equivalent to I alpha, torque 1 plus torque 2, okay, vector, by using vector method, is equivalent to I alpha. This is similar analogy to F external equivalent to MA. We list down all the F external. For example, in this case, we have F1, we have F2, right? So we have to add up F1 and F2 according to the vector technique, equivalent to MA. So similar analogy, right? Example 10.4, rotating rod. A uniform rod of length L and mass M is attached at one end of a frictionless pivot and is freely to rotate about the pivot in the vertical plane as in the figure. The rod is released from rest in horizontal position. What are the initial angular acceleration of the rod and the initial translational acceleration of its right end? So this is our pivot, this is the length of the rod, and this is the weight of it at the center of it. Okay, so we are going to apply sum of torque external equivalent to Fg. This is the one that going to cause the rotation times with R. Okay, so Fg itself is mg. The R, okay, is half of the length because, okay, here is the force and here is the R, okay, which is half of the length. Then, okay, not to forget, it's equivalent to I alpha, right? Okay, so alpha itself must be sum of the torque external over I. Okay, so what is our torque external? Which is mg L over 2. Okay, and the I for a rod, okay, for a rod, okay, where the axis of rotation is at one end, the end of it, okay, is 1/3 times ml squared. Okay, so we can simplify, cancel out the m. We are left with, okay, 3g over 2l. This is our alpha. And now, AT, tangential acceleration, is equivalent to R alpha. And our alpha just now is this one. So what is our R in this case? Okay, our R is the L. Okay, for a circular motion, right? Tangential circular motion. Okay, how about this R? This R is for the top perpendicular distance. Okay, and for this case is about circular, which is this one. The R is the length. This one is this one. Okay. So, we can cancel out the L, and finally we will have, okay, 3 over 2 G. This is our AT and this is our alpha. Right, example 10.6, angular acceleration of a wheel. A wheel of radius r, mass m, and moment of inertia I is mounted on a frictionless horizontal axle as in the figure. A light cord wrapped around, okay, the wheel supports an object of mass m. When the wheel is released, the object accelerates downward. Okay, what else? Okay, the cord unwraps off the wheel and the wheel rotates with an angular acceleration. So the wheel going to experience alpha. Right, next one. Find the expression for the angular acceleration of the wheel, the translational acceleration of the object, and the tension in the cord. Alright. So, we are going to use sum of torque external equivalent to I alpha and also analyze on sum of Fy equivalent to MA. Alright. So, from sum of torque equivalent to I alpha, we want to figure out the alpha itself must be the torque external over the I. So torque external is coming due to the tension. The tension is the one that going to rotate, okay, the disc, isn't it? So what tension T downward like this, and also what is the perpendicular distance, okay, from tension to the axis of rotation O, which is the R, the radius of the disc. That is why we have TR. Where is sin theta? Sin 90. Okay, because it's already perpendicular. So we have TR sin 90 over I. Then, for the sum of Fy, we have for this object, the free body diagram, okay, we have the T is upward, the weight is downward, but not to forget the object is experiencing an acceleration downward. So we are going to choose downward as positive Y so that our A has positive sign. So we were going to have mg positive minus T equivalent to MA. A here is also the AT because it's tangential, okay, to the disc here. Right, so from here, rearrange the A or AT is equivalent to mg minus T over M. Right, and not to forget that our A here or AT here is equivalent to R alpha. And our A from here is TR over I. So dot with the R, so you have TR square over I. And from translational motion of this block, okay, AT also equivalent to mg minus T over M. So equate this equation. Okay, if let's say our interest in T, then rearrange the equation to make up for T, Or you may also rearrange the equation, put the A as our unknown, right? So bear in mind that alpha is equivalent to AT over R. So if we want to figure out the alpha, we may use this one. So you will have this kind of equation. What if the wheel were to become very massive, so that I become very large? Okay, what happens to the acceleration A of the object and the tension T? If the wheel becomes infinitely massive, okay, we can imagine that the object of mass m that hanging, okay, will simply hang from the cord without causing the wheel to rotate, because the m is less mass compared to the wheel, right? So we can show that in mathematics, okay, by taking the limit of I to the infinity, because the I is so massive, right? So the equation 5, okay, will be like this, right? Limit of, okay, G, okay, this is for A, right? Okay, G over 1 plus I over mr squared. So we are going to take this limit of equation where the I is approximately or approaching to the infinity. So if this part become infinity, let's imagine this. So if the I is infinity, infinity divided by something, it's infinity, right? So G divided by infinity, you have 9.8 divided by the infinity number, it become 0. Okay, so A will be 0. What does that mean? No movement of the hanging block. Okay, so the wheel will not rotate, right? And how about the T? Okay, again, we are going to take the equation T and take the limit of it. Okay, the limit of mg over I plus mr squared over I. Okay, when the I is approaching infinity again, if your I become infinity, okay, what will happen to this equation? Mr squared divided by infinity, it is 0, isn't it? Then 1 plus 0, mg over 1 means only left with mg. So it is balanced with the weight. The T is balanced with the weight. Okay, give the same meaning that there is no motion, no movement. Okay, this is what is the meaning of our finding here. Right, example 8.14. Okay, the falling bucket. A solid, uniform, frictionless cylindrical reel of mass m equivalent to 3 kg and radius r equivalent to 0.4 meter is used to draw water from a well. A bucket of mass m equivalent to 2 kg is attached to a cord that is wrapped around the cylinder. A. Find the tension T in the cord and acceleration A of the bucket. Okay. B. If the bucket starts from rest at top of the well and falls for 3 seconds before hitting the water, how far does it fall? Right. So this is a physical diagram of them. This is the bucket. Okay, free body diagram of it. This is a free body diagram of the reel. Right, for the hanging bucket, okay, we are going to analyze sum of Fy equivalent to MA. What we have there is T upward minus Mg equivalent to MA. And this is going to be our equation 1. For the real, okay, we are going to apply sum of the external equivalent to I alpha. So we are going to apply I for the formula of solid cylinder, which is equivalent to half mr squared. And torque that exists or experienced by the real is actually due to the tension. So T times the perpendicular distance is R sine 90, and the direction is clockwise direction. That is why it has negative sign. Is equivalent to our I just now, half mr squared alpha. And from here, rearrange, okay, so that the T become the unknown or the title. we will have negative half m r alpha, where we know that r alpha is actually A. So this will be our third equation. Substitute equation 1 into equation 3 will give us the A equivalent to negative 5.6 meter per second squared. Alright, once we've got the A, now we can figure out the T by substituting the value of A into equation 3, where it will give us the T equivalent to 8.4 Newton. Right, part B, given to us a time, okay, the question asks for how far the bucket will fall down. So we are going to use kinematics equation, delta y equivalent to V naught yt plus half ayt squared. Since it starts from rest, so V naught y will be 0. And our ay is the A, right? And which is calculated already in part A. Substitute it here and substitute the t as informed in the question, which is 3 seconds. It will give us the delta y is negative 25.2 meter. Okay, the last subtopic here, calculation of moments of inertia. Okay, in simple, we already memorized that moment of inertia is equivalent to mr squared. Okay, but if you have system of discrete particles, means that one system consists of sub particles, okay, that combine become a system. So to calculate moment of inertia of the system is equivalent to sum of r I squared times delta mi. So for every item, okay, that contribute or add up to become a particle. So for continuous rigid object, okay, I is now defined as limit of, okay, ri squared delta mi, okay, whenever the delta mi approaching 0. Means that this is equivalent to integral of r squared, okay, to the respect of m. And we know that density is equivalent to mass over volume. So when we have dm is equivalent to rho dv, because rho is a constant, a fact, right? A constant. Okay. For example, rho for water is 1000 kilogram per meter cube. Okay. So the one that keep going to be changed is the V, the volume. Right. So I also can be calculated by using integral of rho r squared dv.